So our six trigonometric functions have a couple different definitions. We are going to start really with our triangular definition, but I want to put that in context of what we've been talking about so far. We've been talking about angles and rotations and oscillations in terms of things going around in kind of a circular motion. And we are eventually going to put our angles in that circle for definition of our trig functions, our angle theta in either radians or in degrees. These tools will work on both radians and degrees, and we'll use both. And we've talked about the relationship between the radius of this circle and the arc length that the angle produces in terms of defining our radian measure. But there are other lengths in this kind of situation that can often be important. There's, this length here that people might care about. There's this length here people might care about. There's that length, which is just the radius of the circle. There's the length to there. There's a whole bunch of different physical lengths in this thing that one might care about when they're dealing with not only geometric angles, but when they're dealing with other oscillating bodies. So dealing with all of these different kinds of pieces and their relationships while staying in the circle can be a lot to work with. So what we're going to do to start is just grab this triangle here and focus on the relationships in terms of this triangle. And then when we get back to our circular definition, our triangle will fit inside that circle as shown and allow us to extend what we learned about the triangles to angles in a circle. The big important thing about these triangles is that they are nice right triangles. So I'm going to give us over here a nice big right triangle that we can work with. And just like in our diagram over here, there's one of the angles that we're going to, in our triangle, that we're going to care about. There are, of course, three angles in our triangle. There's the right angle. There is the two complementary angles, one down here and one up here, which I'm going to label theta and phi. And the sides of a right triangle have some special names that we're probably somewhat used to. The side opposite the right angle is referred to as a hypotenuse. The other two sides are referred to as legs, but we often reference them in terms of their angles. So I'm going to get rid of theta here and kind of focus, phi, and focus on theta. We refer to the leg that is opposite the angle, the opposite side. And we refer to the side that is up against the angle or makes up the angle as the adjacent side. Now, just really quickly, if we had stuck with phi, then the hypotenuse would still be opposite the 90 degree, but the opposite leg of the triangle would be that one in reference to phi, and the adjacent would be this one in reference to phi. So always be careful. Your adjacent and opposite side, which legs are adjacent and opposite, is dependent on which angle you are referencing. So be a little careful about that. So where our trig functions come from is people notice over time that if you have a triangle with some fixed angle and you look at these lengths, let's say this side opposite that angle is length, say 4, and the hypotenuse is length 5. If we made this triangle larger, if we scaled it up, then yeah, those lengths would change. So this would no longer be a 5 and a 4. This might be a 15 now, and this might be a 12 now. But the ratio between those sides stays the same regardless of what scale we're at. At any scale, that ratio between the opposite length and the hypotenuse, that ratio will stay fixed regardless of how big or small the triangle is. And that should seem reasonable. If I make this triangle twice as big, both the opposite length and the opposite length grew by the same scale, grew by the same amount. So their ratio should be constant. And that ratio between the opposite side and the hypotenuse of a triangle, of a right triangle, has a name. And we call that ratio the sine ratio. So if somebody gave us an angle here and asked for the sine of that angle, we abbreviate the function sin. This is essentially like f of x, but sine of theta. We abbreviate it sin. We should still say sine. So our sine of theta, its job, that function's job, is to output the ratio between the opposite side and the hypotenuse of a triangle with that angle. So that sine function outputs the opposite over the hypotenuse ratio of a triangle. So, for example, if we have a triangle and say that length is 5, this length is 12, and that length is 13, you can verify for yourself that that makes a right triangle. If we have a little angle in here, theta, then the sine of that angle, theta, is going to be equal to the ratio between the side opposite, 5, and the side that's the hypotenuse, 13. So it's going to output 5/13. And this is going to be handy for us because that ratio of 5/13 is going to be true for any triangle that has that same angle in it. No matter how large or small we make that triangle, let's say this was a model that we built where this was 5 inches and 13 inches. If we scaled this up to some massive building where we needed this to be 10 feet high for some roof piece or something, then this side length has to stay in that same ratio. The ratio between the opposite and hypotenuse, our sine, still has to be that 10 feet in relation to this other side. We don't know. And since if I want this angle to match that angle, it would have to stay consistent at 5/13. So we could solve this and find that new length. Now this might seem similar. This might seem like when you worked with similar triangles, when you did other problems in geometry, and it is. Essentially, trigonometry is a somewhat formalized, was it 26? Similar triangle argument that's going to be taken to a pretty extreme degree. Now, we will do a lot fancier things than that, but that's kind of a nice introduction to, that's what these functions are for. They're for taking what values that we know for ratios and applying them in different scenarios based on what that angle is. But the sine function is only one of the possible ratios between these three sides. The opposite in ratio to the hypotenuse is only one of the values, one of the ratios that we could get. One of those lengths in that circle diagram that I looked at that we're interested in. There are other ratios that we might want or might find useful. Another ratio is called the cosine function. We'll talk about why they're called sine, cosine, the other names in a future video. Look for that one, it'll be a fun one. So the cosine function is similar. We will abbreviate it COS. But again, we'll say cosine of theta. So what the cosine function wants to do is it will take in an angle measure, again in either radians or degrees, and output the ratio between the adjacent side and the hypotenuse. Same basic tool, just a different ratio. So if instead of caring about this height, you care about this horizontal displacement in this case, then the cosine might be the right function for you. For my little triangle up here, the cosine of theta, we can put the parentheses or not, would be that, again, that ratio between the adjacent side, the 12, and the hypotenuse, 13. So the cosine value there is going to be 12/13. And we could use that to figure out what this length is in our big triangle if we wanted to. Okay, that's two ratios down. We got the ratio between the opposite to the hypotenuse, the ratio of the adjacent to the hypotenuse. We got a couple more ratios, or a few more ratios we want to look at. The tangent function. I should have just said the cosine, sorry. I should have just said the cosine ratio. The tangent ratio, or function, which we abbreviate TAN. Try not to say tan, so we should be saying tangent. The tangent function gives us a different ratio. Each of these trig functions, that's really all they do. You give these trig functions an angle, and their job is to tell you the ratio between different sides. The tangent focuses on the ratio between the legs, specifically the opposite in ratio to the adjacent legs. So again, in our little red triangle over here, the tangent function would be outputting the ratio between the opposite, 5, and the adjacent, 12. So that 5/12 is the value of the tangent function for that triangle. And thus, any triangle with the same angle in it will have the same ratio in it. Now that's 3 trig functions. How many could we possibly have? Well, we have 6 of them. Now it might seem like we've used all the combinations. We've got the opposite to the hypotenuse, we've got the opposite to the adjacent, we have the adjacent to the hypotenuse. The other 3 combinations aren't different combinations of sides, they change the order of the ratio. So for example, the secant function. Secant ratio, abbreviated SEC, but again we'll say secant function of theta. It outputs Well, technically a ratio we already have, just it's reciprocal. It is the ratio between the hypotenuse and the adjacent side. So we could say here the hypotenuse in ratio to the adjacent, which makes it the reciprocal of cosine. So we'll often see it expressed as 1 over cosine theta, because it is that reciprocal of cosine. There's the cosecant function. Again, we'll talk in a future video about why they're named these. The cosecant function or ratio, abbreviated CSC, cosecant, is again one of the ratios we already have, just in a reciprocal order. So it is the hypotenuse in ratio to the opposite. So we often just think of it as the reciprocal of the sine function. Well, we have a reciprocal for sine, a reciprocal for cosine. The last one, you might have guessed, is the reciprocal for tangent. And it is referred to as the cotangent function or ratio. Abbreviated COT for cotangent. And the angle or the ratio is just that reciprocal for tangent. Adjacent over opposite. And we often think of it, again, in terms of just being the reciprocal of tangent. So we will primarily focus on these first three. Most of the jobs we do can be done with those first three tools. These reciprocal tools are often thought of as kind of our secondary Pythagorean identity, not Pythagorean identity, sorry, our secondary functions. We'll use them a little less often, and often when we do use them, we will simply use them as the reciprocal of the others. But if we wanted to kind of finish this out over here, we've got the sine of that angle theta is the 5/13. The cosine of this angle theta is the 12/13. The tangent, the 5/12, the opposite over adjacent. The secant would be the reciprocal of cosine, so it would be 13/12. Cosecant would be the reciprocal of sine, so 13/5. And the cotangent would be the reciprocal of tangent, so 12/5. So one of the early types of problems that you'll be asked to do is if somebody gives you a triangle that is a right triangle, and you know side lengths on it. So say you know this is length 5, and this is length, 7. Given an angle of reference, we'll call that theta, determining what the sine of theta, what the cosine of theta, what the tangent of that angle theta, what the, I'm going to go cosecant first. Cosecant of theta, secant of theta, and cotangent of theta are. Finding each of those values is a common early question in getting used to these trig functions. So let's go through that real quick. Again, the sine, we know the sine is opposite over hypotenuse. The opposite length in reference to that angle is the 5, but we don't know the hypotenuse. Well, luckily, you hopefully remember we have a tool that relates the legs to the hypotenuse in a right triangle. we've got good old Pythagorean theorem. The sum of the squares of the legs of a right triangle is equal to the square of its hypotenuse, no matter what we label them. So 5 squared plus 7 squared is the square of that hypotenuse. So 25 plus 49 is the square of our hypotenuse. So what, 74 is c squared. So that's going to make c plus or minus, don't forget the plus or minus, the square root of 74. Because we're dealing with just a physical length in our triangle, we will go ahead and just use the positive. But do be careful when we get back to that circle in xy coordinates, those negative values are going to take on meaning. So don't forget that plus or minus is there. Oftentimes we will need it. No reason to approximate the square root of 74. It's a nice exact value, so we're going to keep it. So it's going to be 5 over the square root of 74. You do want to rationalize your fractions. It's a good habit. It's very polite to rationalize your fractions. So the sine of that angle theta is 5 square root of 74 over 74. Really, once we have that other side, the rest of them should go pretty fast. Our cosine function, we remember that's adjacent over hypotenuse. It does take a little while to get these all down. But the adjacent side to that angle is 7 in ratio to the hypotenuse, the square root of 74. So 7 over the square root of 74, which you will rationalize. If you need to review rationalizing fractions, go for it. Tangent, opposite over adjacent. So our opposite to our angle theta is 5, our adjacent is still 7, so 5/7. We could continue in the same way to do cosecant, secant, and cotangent, but since we often think of cosecant, secant, and cotangent as in terms of being reciprocals of the others, that can even just be a handy way to do it. We know cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Those arrows got a little messy. But either way, our cosecant is going to be the reciprocal of this sine. I'm going to go back to this unrationalized form and use its reciprocal just because that's easier. Let's square root of 74 over 5. Secant, reciprocal of cosine. So square root of 74 over 7. Cotangent, reciprocal of tangent, 7/5. So that really is what the 6 primary trigonometric functions, or the 6 trigonometric functions, are supposed to do. That's their job. Their job for all the trig functions, you will often see me generalize our trig functions, just trig function of theta. So any of the trig functions, they take in an angle. I'm even going to write that. They take in an angle and they give out a ratio of lengths. That's the trig function's job. If we have an angle and want to know the ratio between our sides, that's the job of our trig functions. Now, often in practical applications, we will know this angle. Let's say this angle was 30 degrees or pi over 6 radians, if we're going to be in radians, which we often will be. And let's say we knew this height was, this height here, let's say it's some sort of, building, and the height to the roof of that building is, I don't want 30. How about 24 feet? And somebody wants to know, well, how far is this distance? Well, that's what our trig functions are supposed to do. We know that the sine of that 30 degrees is going to be the ratio between the opposite side, that's the 24, in ratio to the side we want, this unknown hypotenuse. I'm just going to write hypotenuse there. And why did I pick the sine function? Well, because I was told the opposite side, you want the hypotenuse, and that's what the sine function does. It tells us relationship between opposite and hypotenuse. So we picked sine. If we had known the adjacent side or wanted the adjacent side, we might have picked cosine or tangent. But we can solve this equation for that hypotenuse. I'm just going to call this x for ease here. If we want to solve that for x, multiply both sides by x, because having what you're solving for in the denominator is problematic. So we'd have x times whatever the sine of 30 degrees is, equals 24. Divide both sides by the sine of 30 degrees. Again, that's just some number. We'll find out what that number is in a minute. So x is equal to 24 divided by the sine of 30 degrees. Now, 30 degrees happens to be a very nice angle, particularly for the sine function, but it doesn't have to be. This value for sine, cosine, tangent, any of them, of an angle, we will ask the calculator to tell us what that known ratio is, and we will just use that ratio value. So often we'll just, you even grab your calculator and say, okay, tell me what 24 divided by the sine of 30 degrees is, making sure you're in degree mode, and it would spit out this answer. But as I said, sine of 30 degrees is a very nice one. You'll learn the nice ones. The sine of 30 degrees happens to be exactly 1/2. So if we wanted to simplify this, we'd get 48. Again, if it was a nastier number, we'd get a nastier answer, and that's okay. So it would be 48 feet. So that distance is 48 feet. It's a nice early trig type question. Again, we'll get a lot more fancy than this as we go along. But even just this is a surprisingly powerful tool, not just in things like architecture and drafting and engineering and physics, but in a lot of other kind of surprising places, in electronics, in electronics, in optics, in audio, in all kinds of different fields, use these tools in a lot of different ways. Okay, go play with this material. Let me know how it goes. If you have any questions, let me know. And as always, have a wonderful day.